Yogah Karmasu Kaushalam.
Hello everyone, myself Dr. Aditya M, working as an Associate Professor, Department of Physics, Gujarat University, Ahmedabad. Today I am going to talk about fundamental aspects of solid-state physics. Plan of my presentation is, first I would like to say about the aim of the solid-state physics. What is solid-state physics? Significance of solid-state physics. Why we study solid-state physics? Overview of the solid-state physics, and finally the references. So first start with the aim of the solid-state physics. Generally, solid-state physics explains the properties of the solid materials as found on the earth. These properties are expected to follow from the Schrodinger equations for a collection of the atomic nuclei and the electrons interacting with the electrostatic forces. So the fundamental laws governing the behavior of the solids are well known and well tested by using the solid-state physics theory. So question arises in our mind that what is solid-state physics? Generally, solid-state physics explains the properties of the solid materials. It explains the properties of the collection of the atomic nuclei and electrons interacting with the electrostatic forces. It formulates the fundamental laws that govern the behavior of the solids. It is the study of the rigid matter or solids through the different theoretical methods such as the quantum mechanics, crystallography, electromagnetism, and metallurgy. So it is the largest branch of the condensed matter physics. Solid-state physics studies how the large-scale properties of the solid materials which result from their atomic scale properties. Hence, the solid-state physics forms a theoretical basis of the material science. It also has the direct applications, for example, in the technological aspects of the transistor and semiconductors, nanomaterials, and so on. Nowadays, the solid-state physics are also known as the condensed matter physics. It is the study of the behavior of atoms when they are placed in close proximity to one another. In fact, the condensed matter physics is a much better name since the many of the concepts relevant to the solids are also applicable to liquids. Therefore, the solid-state physics nowadays, it is generally known as a condensed matter physics. Significance of the solid-state physics. Understanding the electrical properties of the solids is right at the heart of the modern society and technology. The entire computer and electronics industries, which relies on tuning of the special class of materials, for example, the semiconductor, which lies right at the metal insulator boundary. And one can say that the solid-state physics provide a background to understand what goes on in the semiconductor. Solid-state physics, actually, it is something like that the applied physics, or you can say that it is associated with the applied physics in such a way that as we are considering the new technological aspects, particularly in the future, it will inevitably involve developing and understanding new classes of the materials. So the SSP, it is the applied physics associated with the technological aspects rather than the fundamental aspects. Why we study the solid-state physics? For studying the electronic properties, for studying the electron-phonon interaction, for studying the electron-phonon interaction, particularly in the piezoelectric materials, electron spin charge interactions, particularly in the spinotronics and quantum computations, highly correlated electronic system, particularly in the superconductors. So for that part, okay, one can study the solid-state physics. Now the introduction part. So introduction part are divided into the three sections. Section 1 is the crystallographical structures. Section 2 is the interatomic forces. and section 3 is the crystal dynamics. So section 1 related to the crystal structure. We are very knowing very well that particularly in the part of the elementary crystallography, the solid materials are having the different forms of crystalline, polycrystalline, amorphous, non-crystalline, etc. So first we discuss about what is crystallography, what is crystal lattice, what is crystal structure, different types of lattice, and finally the unit cell. So typically the different crystal structure, when we are considering the different crystal structures in the three-dimensional way, the 14 brevis lattice and the 7 crystal systems, okay, are identified in the crystal structure theory. So as we are knowing very well that the matter particularly is divided into the 3 major parts: gases, liquids and liquid crystals, and finally the solids. You can see that the different ionic variation in all these 3 different parts of the material. In gases, the ions are the randomly distributed in the space. Liquid and crystal, it is more general way. Particularly, it is the ionic movement of the ions, plus and minus ions. And solids, all the ions are fixed at that particular certain position. Now the classification of the solid. So solid materials are classified into the 3 different parts: crystalline, polycrystalline, amorphous means non-crystalline. So all these are having the different examples are seen in the particular picture. Crystalline materials are also known as the single crystal. So you can see that in the picture of the single crystal, picture of the polycrystalline material, picture of the amorphous or non-crystalline materials. So first we discuss about what is crystalline solids. The crystalline materials are known as the solids with an atomic structure based on a regular repeated pattern. The majority of all the solids are the crystalline. So more progress has been made in understanding the behavior of the crystalline solids than that of the non-crystalline materials. Since the calculations of that material are easier than the non-crystalline material, understanding the electronic properties of the solids is right at the heart of the modern society and technology. Here in this slide, you can see that the electrical resistivity of the 3 solid state of the carbon. So 3 solid state are particularly related to the metallic structure, insulator structure, and superconductor structure. So here you can see that each 3 states of the carbon element each contain a system of atoms, spatially electrons of the similar density, and the plot thickness. You can see that the graphite, it is a metal, while diamond, it is an insulator, and Buckminster or Florence, it is a superconductor. So here you can see that the variation of the electrical resistivity with respect to the temperature. In metallic part, you can see that as temperature increases, resistivity increases. Insulator part, resistivity decreases, and the superconductor, you can see that the resistivity becomes up to certain temperature becomes 0 and then increases. So you can see that how the electrical resistivity varies, particularly in the solid state of the carbon elements. Now the single crystal. The single crystals have a periodic atomic structure across its whole volume. So at long range length scales, each atom is related to every other equivalent atom in the structure by their translational or the rotational symmetries. You can see that the symmetrical structure of the single crystal. And the next figure, this third figure, it is the single pyrite crystal, and the below the crystal, it is the amorphous solids. You can see that. So polycrystalline solids. So polycrystalline materials are made of the aggregate of the many small single crystals. It is also called the crystallites or the grains. So polycrystalline materials have a high degree of order over many atomic or molecular dimensions. The grains, or you can say that the domains, are separated by the grain boundaries. So the atomic order can vary from one domain to the next. The grains are usually 100 nanometer to 100 microns in particularly diameter wise. So polycrystals with the grains less than the 10 nm in diameter are known as the nanocrystalline materials. So here you can see that the atomic arrangement of the polycrystalline materials and their the photographic structure, and then finally the grain boundary of this atomic arrangement of the polycrystalline material. The next one is the amorphous or the non-crystalline materials or the non-crystalline solids. So these solids are made up of the randomly oriented atoms, ions or molecules that do not form the defined pattern or the lattice structure. So amorphous materials have order only within a few atomic or molecular dimensions. So generally, these materials are fabricated when we are melting the solids at their melting temperature, and then they conchize this material. At that time, we can generate the amorphous materials. So amorphous materials do not have any long range order, but they have varying degree of short range order. Examples of these amorphous materials include amorphous silicon, plastics, and glasses. So amorphous silicon can be used in particularly solar cell application and the thin film transistor. So here you can see that the atomic arrangement wise of the amorphous material in this particular the three figures. So next one is what is crystallography. So crystallography, it is a branch of science that deals with the geometric description of the crystals and their internal atomic arrangement. So it's important the symmetry of the crystal because it has a profound influence on its properties. So the structure should be classified into different types according to the symmetries they possess. Here the energy bands can be calculated when the structure has been determined. So when the structure has been identified, then you can study the energy bands of that particular material, and according to this energy band you can explain whether these materials are the metallic nature, insulating nature, or the semiconductor nature. Here you can see that the different type of crystals seen in the particular three different figures. So what is crystal lattice? In crystallography, only the geometrical properties of the crystal are of interest. Therefore, if one replaces each atom by a geometrical point located at the equilibrium position of that particular atom, then you can get the crystal lattice. Okay, so here you can see that the platinum crystal. So in the second figure, you can see that the platinum surface, particularly it is the STM photographic nature of the platinum. And the third figure represents the crystal lattice and the structure of the platinum, internal structure of the ionic structure of the platinum. So what is an ideal crystal? An ideal crystal, it is a periodic array of the structural units such as the atoms or molecules, and it can be constructed by the infinite repetition of these identical structural units in space. So the structure can be described in terms of the lattice with a group of atoms which are attached to each lattice point, and finally the group of the atoms, it is known as the basis. Okay, so the lattice plus basis is constructed the crystal element. So brevis lattice. In solid state physics, the infinite array of the discrete points with an arrangement and the orientation that appears exactly the similar one from any of the points, okay, the array is viewed from the any of the points, okay, you can get the structure of the crystals. So a three-dimensional Brevis lattice consists of all points with the position vector R that can be written as a linear combination of the primitive vectors. So the expansion coefficient, it must be having the integers, not the real one. So here you can see that the crystal lattice plane, an infinite array of the points in the space. Each point has identical surrounding to all others. So arrays are arranged in a periodic manner. You can see that the vectors are okay seen in that particular picture. Okay, you can see that the vector A and vector B, okay, in particularly xy plane, and this vector are generated the angle alpha. So this is the ideal picture of the crystal structure. The crystal structure can be obtained by attaching the atoms or group of atoms or molecules, which are called the bases or motif, to the lattice, sides of the lattice point. Okay, so the crystal structure is nothing but it is the crystal lattice plus bases. So here dark circle represent the crystal lattice and the colors circle are represented the basis point. So here you can see that both the terms are associated because the crystal lattice, it is a particular point. So this the basis materials are okay put at that particular crystal lattice points and generate the crystal structure of each of the material. In 2D Brevis lattice with a different choice of the basis, here you can see that the right hand side, the Brevis lattice point plus the basis, okay, and the crystal. So according to the Brevis lattice points, okay, the basis should be okay put, or you can say that they are fixed at that particular position and generate the crystal structure. This is the two-dimensional view of the crystal. Generally, 5 Brevis lattice in two-dimensional. Particularly, first one is the general one, then rectangular, then square, then centered rectangular, then hexagonal. According to their periodic arrangement, okay, the unit cell is constructed in two-dimensional in the following way. Let us the smallest component of the crystal, or you can say that the group of atoms or ions or molecules, which when stacked together with the pure translational repetitions, which reproduces the whole crystal. Here you can see that the unit cell of the material S, and the next figure is the 2D crystal. You can see that how the unit cell is generated in that particular direction. So it is the repeated way. Repeated motion is okay. Repetition is generated. According to the repetition, you can construct the different okay combination of the unit cell. Now this slides gives the ideology of the how the unit cell in three-dimensional are seen. This is the three-dimensional picture of the unit cell. Generally, the three common unit cells in 3 dimensions. First one is the simple cubic, second one is the body-centered cubic, and third one is the face-centered cubic. You can see that all these the unit cells according to their atomic position. So unit cell is something like that. When we are considering the entire lattice, the unit cell is uniquely determined by these 6 lattice constants: A, B, C, alpha, beta, and gamma. A, B, C are the vectors related to the XYZ plane, and alpha, beta, gamma is nothing but it is the angle generated according to this particular vector points. So only the 1/8 of each lattice points in a unit cell can actually be assigned to the cell. So each unit cell in the figure can be associated with the height plane. Height multiplied by 1/8 is equal to 1 lattice point. So 1 lattice point is calculated or is identified by this way. Now we move over the typical crystal structures in the three-dimensional way. So as I have told you earlier that we have the 14 Braves lattice and the 7 crystal types. First one is the cubic crystal system, in which the simple cubic, body-centered cubic, face-centered cubic. Then second one is the hexagonal crystal system, is the simpler one. Triclinic crystal system, monoclinic crystal system, orthorhombic crystal system, tetragonal crystal system, trigonal means rhomboidal crystal system. So these are the 7 crystal systems or 7 type of crystals. Here you can see that the 14 different Braves lattice according to the 7 different types of systems: cubic, tetragonal, orthorhombic, hexagonal, monoclinic, triclinic, trigonal, etc. So total, okay, according to the atomic arrangement of the particular, okay, atoms or molecules in the lattice plane, okay, we can get the 14 Braves lattice. So here, the simplest example for constructing the sodium chloride structure. So sodium chloride, it is a crystalline material in a cubic lattice, but with a different unit cell, because here this particular material is based on the 2 different, okay, materials, Na and Cl, Na plus and Cl minus ions. So sodium chloride structure consists of the equal numbers of the sodium and chlorine ions, which is placed at the alternative points of the simple cubic lattice. So each ion has 6 of the other kind of the ions as its nearest neighbors. So here in this particular slide, you can see that how the NaCl atoms are constructed. Okay, so first one, first figure, it gives the ideology about the how the Na plus and Cl minus ions are attracted with each other after transferring the electronic, okay, after transferring the electrons and constructing the NaCl electrons. So different types of NaCl ions are constructed in the figure number 3, and finally it produces the crystal structure of the NaCl, and the last figure gives the idea of the how the NaCl crystal is seen. Now the second section of my talk is the interatomic forces. So what kind of forces hold the atoms together in a solid? Particularly the energies of the interaction between the atoms. So the ionic bonding is produced. Particular example is the NaCl. Covalent bonding is produced. Comparison of the ionic and covalent bonding. Metallic bonding is produced. Van der Waals bonding is produced, and hydrogen bonding is produced. According to this different type of bonding, okay, it is associated with the how the interatomic forces are generated between the 2 ions in the crystal structure. So energies of the interaction between the atoms, how the energy should be transferred from one atom to the another. So the energy of the crystal is lower than that of the free atom by an amount of the equally to the energy required to the pull and crystal apart into a set of the free atoms. So this type of energy is known as the binding or cohesive energy of the crystal. Generally, when we are considering the example of NaCl, it is more stable than the collection of the free Na and Cl atoms. In Ge crystal, germanium crystal is more stable than the collection of the free Ge. Here you can see that how the Cl atoms are transferred their energy to the Na, and finally the NaCl atoms, okay, binding energy of the NaCl atoms, okay, generate the NaCl crystals. The types of the bonding mechanisms. It is conveniently, you can say that the classification of the bonds between the atoms into the different types are related to the ionic, covalent, metallic, van der Waals, and the hydrogen. So all bondings is a consequence of the electrostatic interaction between the nuclei and the electrons. So in this slide, you can see that the different types of bonding and their properties or the characteristics with the example. So the types of bonding, it is differentiated in the 5 different bonds: ionic bonding, van der Waals bonding, metallic bonding, covalent bonding, hydrogen bonding. In ionic bonding, it has the high melting point, hard and brittle one, non-conducting solid. Example of this one is the NaCl, CSCl, ZnS, etc. In van der Waals bonding, it is having the low melting points, soft and brittle, non-conducting one. So here, these are the different, the gaseous elements like neon, argon, krypton, xenon. Metallic bonding are variable with their melting point of the material, variable hardness. It is related with the conducting one. For example, the ferrous, copper, silver. These are the example, metallic, nature of that particular metallic bond. Covalent bond, it has very high melting point, very hard one, usually not conducting one. So diamond and graphite are the structure which are having the covalent bond. Hydrogen bond, it is the low melting points, soft and brittle one, usually non-conducting. The example is the ice, organic solids. These are the example of the hydrogen bonding. So here you can see that how the different types of bondings, are having the different properties. So first we discuss about the ionic bonding. So ionic bonding, it is the electrostatic forces of the attraction between the positively and negatively charged ions between the non-metals and the metals. So all ionic compounds are the crystalline solids at room temperature. So NaCl, it is a typical example of the ionic bonding. So here, the metallic elements have only up to the valence electrons in their outer shells. So when losing their electrons, they become positive ions. So electronegative elements tend to acquire additional electrons to become the negative ions, or you can say that the anions. So here the figure sees that how the one electron should be transferred from the Na to Cl ions. So when the Na plus and the Cl minus ions approach each other closely, so that the orbits of the electrons and the ions begin to overlap with each other, then the electrons begin to repel each other by the virtue of the repulsive electrostatic Coulomb force. So this type of closest phenomenon together, the ions are greater the repulsive force. So generally, the Pauli's exclusion principle has an important role in the repulsive force. To prevent a violation of the exclusion principle, the potential energy of the system increases very rapidly. covalent bonding. Covalent bonding takes place between the atoms with the small differences in electronegatively and which are close to each other in the periodic table. Particularly, the elements are put in these two groups, non-metallic and non-metal groups. The covalent bond is formed when the atoms share the outer shell electrons, that is S and P electrons, rather than by the electron transfer. So here the S and P electrons are associated with each other and generating the covalent bond. So noble gas electron configuration, it can be attained. Okay, so here you can see that the formula of methane, okay, CH4 structural formula. So the carbon should be bounded with the covalent bond, particularly with the H element. And generally, the nature of the structure is seen in the ball and stick model and the space filling model. How all these atoms are connected with each other by the covalent bonding. So here, each electron in a shared pair is attracted to both the nuclei involved in the bond. So the approach of the electron overlap and attraction, it can be visualized as seen in the following figure. You can see that, which is representing the nucleon electrons in a hydrogen molecules. So how the covalent bonding is generated. Now the comparison of the ionic and covalent bonding. Here you can see that in the covalent bond, when the two atoms are repelled with each other, means sharing of the electrons with each other, then generate the covalent bond. And the next figure you can see that the covalent bond is generated between the two atoms like the following way. But in the ionic bond, here the transfer of the outermost electron to the another atom generate the ionic bond. So the ionic bond actually, it is associated in the particular the outermost part of the two ions, outermost orbit of the two ions. Now metallic bonding. So metallic bonding is found in the metal elements. It is the one type of electrostatic force of the attraction between the positively charged ions and the delocalized outer electrons. So the metallic bond is weaker than the ionic and the covalent bonds. So here the metal, it may be described as a low density cloud of the free electrons. Therefore, the metals have high electrical and thermal conductivity. Here you can see that the black circle actually is nothing but it is the electrons, free electrons, which are associated with the positive ions. So free electrons are moved freely from their outermost orbit and generate the metallic bonding. So here two ions are generated with the metallic bonding. Next slide is the van der Waals bonding. So generally, these are the weak bonds with the typical strength of 0.2 electron volt per atom. So these bonds occur between the neutral atoms and the molecules. Generally, the van der Waals forces, it is a weak forces of attraction, result from the neutral fluctuations in the electron density of all the molecules that causes the small temporary dipoles to appear within the molecules. It is, one can say that the temporary dipoles that attract one molecule to another, and therefore this type of the attractional force is called the van der Waals force. The shape of the molecule influences its ability to form a temporary dipoles. Here you can see that the structure of the dipoles in the figure. So long thin molecules can pack closer to each other than the molecules and that are more spherical. So here you can see that the spherical bond is generated. The bigger the surface area of the molecules, the greater the van der Waals forces will be, and the higher the melting and the boiling points of the compound will be. So the van der Waals forces are of the order of 1% of the strength of the covalent bond. So in this particular figure, you can see that the homomolecular molecules, such as the iodine, which develops the temporarily dipole due to the natural fluctuation of the electron density within the molecules. And the second figure shows the heteronuclear molecules, such as the HCl, have the permanent dipole, and that attract the opposite pole in the other molecules. So here opposite, the molecules are bonded, with each other with the van der Waals attraction. So van der Waals forces are due to the electrostatic attraction between the nuclei of the ion, nuclei of the one atom, and the electrons of the other atom. So this van der Waals interaction occurs generally between the atoms which have the noble gas configuration. Next one is the hydrogen bonding. A hydrogen atom having a one electron, it is the first element of the periodic table. It can be conveniently bounded to only a one atom. So however, the hydrogen atom can involve itself in an additional electrostatic bond with a second atom of a highly electronegative character, such as the chlorine or the oxygen. So this second bond permits the hydrogen bond between the two atoms of the structure. The strength of the hydrogen bonding varies from 0.1 to 0.5 electron volt per atom. So the hydrogen bonds connect water molecules in ordinary ice structure. So hydrogen bonding is also very important in the protein structure and the nucleic acid structure. Therefore, this hydrogen bonding are very much important in the life, different type of life related processes. The section 3 of my talk is related with the crystal dynamics. So here one can study the different properties of the crystals, the sound waves, lattice vibration of one-dimensional crystals, particularly chain of the identical atoms, chain of two types of atoms, lattice vibration of the 3D crystals, phonons, heat capacity from lattice vibrations, and harmonic effects, thermal conduction by phonons. So what is crystal dynamics? Atomic motion are governed by the forces exerted on the atoms when they are displaced from their equilibrium positions. So to calculate the forces, it is necessary to determine the wave function and the energies of the electrons within the crystals. And fortunately, many important properties of these atomic motions, it can be deduced without doing these calculations. For example, Hooke's law. So one of the properties of the elasticity is that it takes about twice as much as force to stretch the spring twice as far. So this linear dependence of the displacement upon the stretching is called the Hooke's law. Here you can see that the spring, the one end of the spring is connected with the fixed element, and the next end of the spring is connected with the ball and generate the force. So this force generated in spring is F spring is equal to minus kx. K nothing but it is the spring constant. Is the massless spring. Now the sound waves. So the mechanical waves are particularly the waves which propagate through a material or the medium, and the medium a medium is the solid, liquid, or gas at a wave speed, which depends on the elastic and inertial properties of the medium. So there are the two basic types of the wave motion for the mechanical waves. One is the longitudinal and second one is the transverse. So it corresponds to the atomic vibration with a long lambda. Lambda is nothing but it is the wavelength of the wave. So presence of the atoms has no significance in the wavelength limit, since the values of this lambda is very much greater than their atomic constant A. So there will be no scattering due to the presence of the atoms. Here in these two particular figures, you can see that the motion of or the propagation of the waves, okay, particularly in our medium. First figure represents the motion of the direction of the longitudinal wave, and second one gives the ideology about these transverse waves. So sound wave propagates through a solids, which tells us that the wave-like lattice vibration of the wavelength, which is very long compared to the interatomic spacing, are possible. So the detailed atomic structure is unimportant for these waves, and their propagation is governed by the macroscopic elastic properties of the crystal. So at a given frequency and at a given frequency and in a given direction in a crystal, it is possible to transmit three sound waves, okay, which are differing in their direction of the polarization and in general also in their velocity. So the important parameter for studying the sound wave properties is the speed of sound waves. The speed of sound waves, particularly in the longitudinal waves, move through a liquid density rho. So it is given by VL is equal to lambda into nu is equal to under root C by rho. C is nothing but it is the elastic bulk modulus and rho is the mass density. So the velocity of sound is in general, it is a function of the direction of the propagation in crystalline materials. So the solids will sustain the propagation of the transverse waves, which travel more slowly than the longitudinal waves. So the larger the elastic molecules and smaller the density, the more rapid can sound waves travel. So here you can see that in this particular slide, the speed of sound for some typical solids, okay, it is compared with the speed of sound observed. Okay, so different materials, you can see that calculated wave speed as well as the observed wave speed. So as we are comparing each of the result, you can see that both the sound waves, both the velocity of the sound waves or wave speed are associated or qualitatively, okay, comparable with each other. A lattice vibration wave in a crystal, it is a repetitive one and systematic sequence of the atomic displacement of a longitudinal wave, a transverse wave, or some combination of the two. So they can be characterized by a propagation velocity nu, wave vector lambda or wave vector, wavelength lambda or wave vector, a frequency nu or angular frequency omega is equal to 2 pi nu. So the equation of motion for any displacement, it can be produced by means of considering the restoring forces on the displacement atoms. As a result, we can generate a dispersion relationship between the frequency and the wavelength, or between the angular frequency and the wave vector. So according to this, you can study the elastic properties of that particular materials. Now, first we discuss about the monoatomic chain. So the simplest crystal, it is one-dimensional chain of the identical forms. This is the one-dimensional picture of the identical atoms. This chain consists of a very large number of identical atoms with the identical mass. So all the atoms are having the identical mass, all the atoms are separated by the distance A, atomic distance A. So atoms move only a direction parallel to the chain. Here you can see, if we are imagine all the atoms are connected with the spring and produces and given the force to the in one direction, then all the atoms are vibrate, according to their vibration. So only nearest neighbor interacted with the previous component. So short range forces are generated. So here the UN minus 1, UN minus 2, UN plus 1, UN plus 2. These are the force generated. Short range force is generated according to this shifting nature, vibration produced in the monoatomic chain. Now this is the chain of the two type of atoms. The two different atoms having the different masses, capital M and small m, are connected by an identical spring of the spring constant K. Then it produces the chain of the two types of atoms, 2D chain. So this is the simplest possible model of the ionic crystal. Here A is the repeated distance and the nearest neighbor separation of this particular our assembly is the A by 2. Now normal mode frequencies of the chain of the two type of atoms. So here in the A point, it is the two atoms are oscillated in the antiphase with their center of mass at particularly rest. B is nothing but it is the lighter mass M is oscillating and M is at the rest. And C point is nothing but here the heavier mass M is oscillating and small mass M is at rest. So this is the dispersal relation between the frequency, angular frequency versus K. So if the crystal contains the n unit cells, we would expect to find the 2n normal modes of vibrations. And this is the total number of atoms and hence the total number of equations of motion for mass M, capital M and the small m. So as there are two values of the omega, for each value of K, the dispersion relation is said to have the two branches. First branch is known as the optical branches and second branch is the acoustical branches. You can see in the particular figure also. So upper branch is due to the positive sign of the root and the lower branch is due to the negative sign of the root. So the dispersion relation is periodic, particularly in the wave vector K with a periodic boundary 2 pi by A, means 2 pi by unit length. So this dispersion relation is studied in the particularly the Brillouin zone, first Brillouin zone. So this result remains valid for a chain containing an arbitrary number of atoms per unit cell. So now let us discuss about the acoustic and optical branches. The acoustic branches, as its name suggests, that it gives the rise to long wavelength vibration, means speed of sound is in rising mode. An optical branch, it is a higher energy vibrations, so the frequency is higher. You need a certain amount of energy to excite the mode. So here the term optical comes from how these were discovered. So notice that if atom number 1 is positive and atom number 2 is negative, then the charges are moving in opposite direction. According to this one, the variation of this opposite direction, the ideal picture of this one seen optically, therefore it is known as the optical branches. So in this picture, you can see that the transverse optical mode for diatomic chain. Here the amplitude of the vibration is strongly exaggerated. This slide shows the transverse acoustical mode for the diatomic chain. Now, the terminology phonon. So consider the regular lattice of the atoms in a uniform solid materials. So there should be the energy associated with the vibrations of these atoms, but they are tied together with bonds, so they can't vibrate independently. So the vibration is taken in the form of the collective modes, which propagate through the material. So such a propagating lattice vibration, it can be considered to be the sound waves, and their propagation speed, it is the speed of sound in the material. The vibrational energy of the molecules are quantized and treated as the quantum harmonic oscillators. So the quantum harmonic oscillators have equally spaced energy levels with the separation of the energy delta is equal to h nu. So the oscillators can accept or lose energy only in the discrete units of the energy h nu. So the evidence of the behavior of the vibrational energy in periodic solids is the collective vibrational modes, and it can be accept energy only at discrete amount, and this quanta of energy have been labeled as the phonons. So here in this slide you can see that the two different terminology of phonons and photons. Phonon is nothing but it is the quanta of lattice vibration, and photons is nothing but it is the quanta of electromagnetic radiation. In phonons, the energy of the phonons are quantized. In photons, the energy of the photons are quantized as well. Okay, so here you can see that the energy and the momentum of each of the terms are having the different terminology. Now, first we discuss about the thermal energy and the lattice vibration. So atom vibrate about their equilibrium position. They produce the vibrational waves. So this motion increases as the temperature is raised. Particularly in solids, the energy associated with this vibration and perhaps also with the rotation of atoms and molecule is called the thermal energy. Okay, so here you can, in this particular the figure, you can see that there atoms vibrates at their particular plane and produces the thermal energy. So in a gas, the translational motion of the atoms and molecules contribute to this particular energy. Therefore, the concept of the thermal energy is fundamental to the understanding many of the basic properties of the solids, and which would like to know about what is the value of the thermal energy, how much is available to scatter a conduction electron in a metal, since this scattering gives rise to the electrical resistance. The energy can be used to activate a crystallographic or a magnetic transition, how the vibrational energy changes with the temperature, since this gives measure of the heat energy which is necessary to raise the temperature of the material. Recall that the specific heat or heat capacity is the thermal energy which is required to raise the temperature of the unit mass or 1 gram molecule by Kelvin. Now the next term is the heat capacity from the lattice vibration. So energy given to the lattice vibration, it is the dominant contribution to the heat capacity in the most of the solids. In non-magnetic insulators, it is the only the contributions. Now other contributions to produce the heat capacity is in the particular metallic part from the conduction electrons, and in the magnetic materials from the magnetic ordering. So atomic vibrations lead to the bands of the normal mode frequencies from 0 up to some maximum value calculation of the lattice energy, and heat capacity of the solid therefore falls into the two parts. One is the evolution of the contribution of the single mode and the summation over the frequency distribution of the modes. So here you can see that the graph of the CV is a function of the temperature T. So specific heat CV, it is a constant volumes depends on the temperature. As shown in the figure, CV is the specific heat as constant volume. So at high temperature, the values of CV is close to the 3R, where R is nothing but it is the universal gas constant. And the values of R is approximately 2 calorie per Kelvin into mole. At high temperature, CV is approximately 6 calorie by Kelvin into mole. So this range usually includes the values of RT. From the figure, it is seen that the CV is equal to the 3R at high temperature, regardless of the substance. And this fact is known as this Dulong-Petit law. So this law states that the specific heat of a given number of the atoms of any of the solids is independent of the temperature, and it is the same for all the materials. Now the next terms is the density of states. So according to the quantum mechanics, if a particle is constrained, the energy of the particle can only have the spatial discrete energy values. It cannot increase infinitely from one values to another. So it has to go up in the next step. So these steps can be so small depending on the system that the energy can be considered as continuous. So this is the case of the classical mechanics. But when we are considering this case in the atomic scale, the energy can only jump by discrete amount from one value to another. So here you can see that the different figures of the definite energy levels. In some cases, each particular energy level, it can be associated with more than the one different states or the wave function. So this energy level is said to be degenerative. So the density of states, rho epsilon, it is the number of discrete states per unit energy level, and so that the number of states between the epsilon and epsilon plus delta d epsilon, which will be the rho epsilon into d epsilon. So from this density of states, you can find out, you can study the enharmonic effects. So any real crystal resists comparison to a smaller volume, then its equilibrium value more strongly than the expansion due to the larger volume. So this is due to the shape of the interatomic potential curve. This is a departure from Hooke's law, since harmonic applications does not produce this property. So this is an enharmonic effect due to the higher order terms of the potential, which are here ignoring the harmonic approximation. Thermal expansion, it is an example of the enharmonic effect. In harmonic approximation, particularly phonons, do not interact with each other in the absence of the boundaries. So the lattice defect and the impurities, which also scatter the phonons, the thermal conductivity of in that particular effect is infinite. So in enharmonic effect, phonons collide with each other, and this collision limit thermal conductivity, which is due to the flow of the phonons. So in this slide, you can see that the phonon-phonon collision, the coupling of the normal modes by the unharmonic terms in the interacting forces, it can be pictured as the collision between the phonons associated with the different modes. Okay, so a typical collision process seen here, phonon 1 and phonon 2 are collide with each other and produces the another phonon is produced. So the energy of the newer generated phonon, it is the combination of the energy of these two phonons, or you can say that frequency is the Omega 3 is the frequency related to the newly generated phonon is the omega 1 plus omega 2, and the wave vector is the k1 plus k2. So it produces the h omega 3 is equal to h cut omega 3 is equal to h cut omega 1 plus h cut omega 2. It gives the conservation of the energy. Similarly, h cut k3 is equal to h cut k1 plus h cut k2. It gives the conservation of the momentum. Now the thermal conductivity by phonons. So the flow of the heat takes place from hotter region to a cooler region. Okay, when there is a temperature gradient in a solid way, the most important contribution to thermal conduction comes from the flow of the phonons in an electrically insulating solids. So you can study the different properties like the transport properties in which you can find out the thermal conduction. So transport properties is the process in which the flow of some quantity occurs. For example, the thermal conductivity, it is a transport coefficient and it describes the flow. The thermal conductivity of phonon gas in a solid, it will be calculated by means of the elementary kinetic theory of the transport coefficient of the gases. Now, the electronic band structure. In solid state physics, the electronic band structure, or simply known as the band structure of the solid, describes the range of the energy levels that the electrons may have within it, as well as the ranges of the electrons that they may not have, called the band gaps or the forbidden bands. So band theory actually derives these bands and band gaps by examining the allowed quantum mechanical wave function for an electron in a large periodic lattice of atoms or molecules. So band theory has been successfully used to explain the many physical properties of the solids, such as the electrical resistivity, optical absorption, and forms the foundation of the understanding of all the solid state devices. For example, the transistor, solar cell, etc. So it is difficult to visualize the shape of the bands as a function of the wave vector, as it would require a plot of 4-dimensional space, energy versus kx, ky, kz. In scientific literature, it is common to see the band structure plots which show the values of E and K for different values of K in the along the straight lines connecting symmetry points, often labeled as the gamma point, okay, kappa point, sigma point, and so on. So another method for visualizing the band structure is to plot a constant energy isosurface in wave vector space, showing all of these states with the energy equal to the particular value. The isosurface of the states, which energy equal to the Fermi level, is known as the Fermi surface. So the energy band gaps can be classified using the wave vectors of the states surrounding the band gap. So here you can find out the two band gaps. Direct band gap, it is the lowest energy state above the band gap, has the same K as the highest energy state beneath the band gap. Indirect band gap is the closest state above and beneath the band gap, do not have the same K point. The electronic band structures are usually associated with the crystalline materials, quasi-crystalline materials, and amorphous solids. It may also exhibit the band gaps. Okay, these are somewhat more difficult to study theoretically since they lack of simple symmetry of the crystal, and it is not usually possible to determine a precise dispersion relation. As a result, virtually all of the existing theoretical work on the electronic band structure of the solids has focused on the crystalline materials. So these are some of the methods for studying for computing the band structure of the materials. First one is the nearly pre-electron approximation, tight binding model, KKR model, density functional theory, Green's function method, ab initio GW approximation, dynamical mean field theory, and others theory. For example, the empty lattice approximation, Cronin-Penning model, Kepi model, Hubbard model, etc. These are these slides actually gives the ideology of how the band structures are seen. and how the band gap is produced. So upper part of this one is the according to the optical and the two branches, okay, related to the band structure. Now, to understand how the band structure changes relative to the Fermi level in the real space, the band structure plot is often first simplified in the form of the band diagram. So in band diagram, the vertical axis is the energy, while the horizontal axis represents the real space or wave vector. So horizontal line represents the energy levels, which blocks the represent energy bands, while the horizontal lines in this diagram are strengthened or slant. Okay, then the energy of this level or band changes with the distance. So diagrammatically, this depicts the presence of an electric field within the crystal structure. So band diagrams are useful in relating the general band structure properties of different materials to one another when placed in contact with each other. In this slide, you can see that the band structure of the different materials. In this slide, you can see that the band structure of the different type of materials, 2D materials, for example, the silicon, graphene, okay, MOS2, WSE2, and so on, and the different the metallic and non-metallic component. Now, next slide, it is the gives the some kind of research concept, modern research concept in the solid state physics. So current research topics in solid state physics includes the strongly correlated materials, quasi-crystals, spin glass, high temperature superconductivity, 2D and 3D materials, nanomaterial, etc. These are the some of the sub-branches of the modern research. Okay, modern research occurred in the solid state physics. Okay, these are the references which are used to prepare these presentations. So thank you and namaste.